Good afternoon from India. I think it is good evening from Germany, or from Singapore. It is good evening. We are now going to start our today's webinar on fastening system in concrete construction, which is being organized by the Institution of Engineers India under the aegis of our Civil Engineering Division. Today we have our eminent personalities like our President, Mr. Narendra Singh. Yeah, Narendra Singh is here, and our Chairman of the Civil Engineering Division Board is here. So I am now handing over the screen to Mr. Amal Singh for the next part of the program. I think Mr. Karan Khanna for the next part of the program. So please take over. Am I audible? Hello. Okay.
You are audible.
Yes, sir, you
are audible. Sir, I would like to take this opportunity to thank Institute of Engineers for giving us this platform to come and talk to everybody about post-installed connections. I would now like to invite eminent persons from IEI for the welcome address.
Hello.
Yes, sir, you are audible. You can go ahead.
Good afternoon, ladies and gentlemen. It is my privilege to welcome eminent panelist, Dr. Janicio, Project Manager, Hilti, Germany, Mr. Amal Singh, Marketing Manager, Hilti from Singapore, Mr. Karan Khanna, Manager Software, Hilti from India, Dr. Sapan Bhomik, Chairman, Kate, Institution of Engineers, Engineer V.B. Singh, the Chairman, Civil Engineering Division Board, Dr. Nilanjan Sen Gupta, Director Technical, and other stakeholders attendees. I welcome you all on behalf of Institution of Engineers, which is the largest professional organization of engineers in India. Friends, it is a good opportunity that this webinar has been organized by the professionals who Hilti. It is a very new technology rather and growing technology in today's scenario. Fastening system in the concrete construction has been organized by Civil Division Board under the aegis. On this occasion, I congratulate the organizers for choosing this very relevant subject in the present scenario of advanced technology. As you friends are aware that II has completed 100 years successfully of its establishment in year 2020. Nowadays, we are passing through very tough time due to COVID-2. Three engineers of our country have joined hands with the scientists and medical professionals to provide eminent solution to this complex problem. I wish you all stay safe at home. And the efforts of the Institution of Engineering always has been to keep its member informed about the latest engineering and technological development occurring in national and international arena by conducting technical events involving eminent professionals and over last 100 years, II has provided valuable suggestions to all policy inputs to the policymakers and contributing in the national growth. II conducts webinars, seminars, lectures, etc. on technical and contemporary subjects, sharing knowledge to our members and many professionals attached to this trade. II has conducted about 60 webinars during the pandemic time with participation of wide range of the professionals. I am extremely happy to note that experts from Hilti Engineering have spared their time to enlighten us and our professionals about the use of fasteners in concrete construction. As I remember, they have also published a book on this subject where I also conveyed my message and good wishes to them for this successful publication. But unfortunately, I could not receive that book by today. Waiting a copy from them today also. As far as I know, fasteners are used to join two or more objects together in non-permanent ways. Each project, each project needs different type of fasteners in order to ensure safe and strong bond between the two. More construction, washers, bolts, wedges are used in specific projects. Usage of fasteners is very common in flyovers and multi-story buildings and metro rails system. Friends, it is a very good webinar, no doubt, but engineers are most common for this to design. If the design is failed, everything fail. Lack of knowledge can cause a failure to the fasteners. We eager to hear our experts over this subject. I wish the success of this webinar and thank you very much. Jai Hind. Jai Hind. Thank you, sir.
Thank you, Mr. Narendra Singh, for the welcome address. Let me take this opportunity to assure you, sir, that your copy of the book is on way and will be reaching you shortly. I would now like to invite Mr. V.B. Singh, Chairman of Civil Engineering Division, for his address.
Thank you, Mr. Khanna. Narendra Singh ji, the dynamic president of the Institution of Engineers, under whose able leadership we are marching with a great pace. Dr. Janicio, Project Manager, Codes and Approvals, Hilti from Germany. Mr. Amol Singh, Technical Marketing Manager, Structural, Hilti from Singapore. Moderator of the session, Mr. Karan Khanna, Manager, Software and Services, Hilti, India, and their delegates. A very good evening to all of you. I welcome you all on to this virtual platform, India. Since inception in 1920, the Institution of Engineers India has upheld the mandate of promoting and augmenting the science, practice and business of engineering through a variety of activities like providing insights to policymakers regarding matters related to engineering profession, imparting engineering education for working community in non-formal mode, fostering national and international cooperation in engineering and technology, dissemination and sharing of engineering and technical knowledge through activities on contemporary topics, and encouraging, elevating, and the technical knowledge and practice of individuals and organizations through scholarships and awards. Standing at the crossroads of a country of glorious existence, a little marred by the global pandemic, it was felt appropriate to bethink, introspect, and disseminate ideas, concepts, and best practices in the emerging areas of technology and engineering through virtual platforms, which finally have evolved into Institution of Engineers Technical Webinar Series. Today, we are all excited at the prospect of listening and gaining insights from our distinguished panelists on the use of fastening systems and its evolution in the context of concrete construction. From antiquity to the present day engineering, the built environment has always included designing connections which have only increased in complexity, thus mastering their behavior and ascertaining their exact performance over an acceptable time frame have been closely monitored and comprehensively studied. The modern construction industry is replete with fastenings that connect concrete to concrete, concrete to steel, steel to steel, steel to masonry, among others, each having different behaviors with differing influencing parameters and varying degree of design complexity. Without sufficient information, the plethora of cast institute or post-installed fastening connectings often are designed with poor engineering judgment stemming from a lack of sufficient knowledge on this topic. Understanding the mechanism involved enables the right selection based on environmental conditions, load parameters, and overall suitability when coupled with right design and installation. The diverse range of methods, challenges, and insights in these areas will be discussed in today's webinar. I believe that the Institution of Engineers technical webinar on fastening systems in concrete construction being organized by the Civil Engineering Division Board today will be relevant for practitioners and researchers and will be successful in portraying the fast changing face of geotechnical engineering in the context of traditional and modern challenges. Thank you so much.
Thank you, Mr. V.D. Singh, for your address. I would now like to invite the first panelist for today to talk about connection of reinforced concrete members with post-installed reinforcing bars. Dr. Janicio, Project Manager for Codes and Approvals for Hilti, Germany. Before I hand it over to Dr. Janicio, let me introduce you to him. He graduated in structural engineering at the University of Florence, Italy, and obtained his PhD at the University of Stuttgart, Germany, on seismic assessment and retrofitting of reinforced concrete structures. Dr. Janicio worked as a consultant for 5 years, dealing with qualification, design, training, and quality inspection of fastening systems. Since 2016, he is Codes and Approval Engineer for Hilti. His field of interest include concrete-to-concrete connections, seismic retrofitting, and fastening technology. He has authored and co-authored several publications on these topics. I now hand it over to Dr. Janicio to take it forward and deliver the topic. We cannot see your presentation, Dr. Janicio. We are seeing your home screen.
Yes, I'm trying to share my screen. Should start soon. Can you see it now?
Yes, we can.
Okay. Thanks a lot, Karan, for your kind introduction, and thanks a lot to the Institution of Engineers of India for having me today to give this presentation on post-install reinforcing bar, a system used to connect reinforced concrete members cast at different times. And good afternoon to all participants. Good afternoon, ladies and gentlemen. So I said today I will give you a glance into this technology used to connect concrete to concrete elements. So I will start introducing this technology, talking about the principle of qualification and design of such connection, and then also give a little bit an overview on the behavior under different loading conditions, such as going beyond static loading, meaning seismic action or fire exposure, or extended working life beyond the standard 50 years typically considered. And then I will also give you an overview on some very new advancement in this technology, fruit of the research conducted in this field and still being conducted in this field, together with different universities around the globe. So when we talk about a post-install reinforcing bar, we refer to a system which basically comprises two elements: a reinforcing bar, as we all know, and a chemical mortar. However, to have this reinforcing bar and this chemical mortar, which is used to glue this bar into a pre-drilled hole in a concrete element, is not sufficient to ensure a proper functioning of the connection. In order to ensure that, we need an entire system, which starts from the use of the appropriate drilling machine and drill bits to drill a hole, and the necessary tools to ensure appropriate hole cleaning, and to inject the mortar, possible without formation of air voids, into drilled holes, which can be also quite depth, up to more than 1 meter depth. And obviously, in order to have a reliable installation, the key person is the installer. There is no way around this key person to ensure that this connection work properly. So why do we need a special attention when we talk about the post-install reinforcing bar versus the traditional cast-in reinforcing bar? The reason it's quite simple, but I think it's important to be highlighted also here, is because the loading transfer between the reinforcing bar and the concrete happens in a slightly different way, because we have a mortar layer in between, and these two sketches are basically showing how this loading transfer works. And the interaction between bar, mortar, and concrete is strongly product dependent, and therefore it requires an assessment procedure. Over the last 20 years, there were a lot of research and code development activities to develop reliable product qualification associated then to also a reliable design of such connections. The first research were still in the 90s. At the beginning of 2000, the first qualification documents were published. And as you can see from this time charts, there are still a lot of things going on. So the basic of the qualification of post-install rebar system is based on the demonstration of equivalence between a post-install rebar and a casting bar. And to do so, the main failure mechanisms need to be considered. Meaning, pull out is when a bar is extracted from a bar loaded in tension is extracted from the concrete without significantly damaging it, which typically happens in condition of high confinement and large concrete cover, or splitting, where the ultimate bond is reached by formation of radial cracks starting from the axis of the bar, which is the typical case in the cases of small cover, which is quite typical in reinforced concrete structure, due to the typical detailing of reinforcing bar in concrete element. And obviously, we need to consider also the robustness of the mortar system in order to withstand all the typical environmental aspects that may be encountered during the entire life of the structure. So we start from the hole cleaning, creep behavior, freeze-thaw cycles, high or low temperature, different type of aggressing environment, which may be a typical alkali environment, which is what we typically have for a bar in the concrete, but also acid environment and corrosion protection, as well as sensitivity to cracking of concrete. And then, as already mentioned, we have the installation. We need to have tools which ensure a proper functioning of this gluing system around the bar, considering the most unfavorable situation, such as long embedment, maybe with an overhead installation at minimum or maximum temperature. And the results of the assessment is summarized in this table shown on the right-hand side, where it's shown that a specific mortar system needs to exhibit a minimum confined bond strength for each reinforced concrete strength classes in order to be qualified for the use according to a design bond stress, which is in this table taken from the provision of Eurocode 2 Part 1. For instance, in a concrete C2025, a system need to exhibit at least 10 megapascal bond strength, which is a value which is reduced in order to account all the possible effects of robustness mentioned before, in order to be designed with the typical 2.3 megapascal bond strength, which is used in the Eurocode 2. And so the first question that we have, okay, how do they correlate these two values? So it's important at this point to remind that this 10 megapascal, it's a confined pull-out resistance measured at short embedment, and it's based on an experimental database on casting bars. And while the typical design bond strength that we use in Eurocode code refers, which is a much smaller value, not only because it is a design value, not a mean value, but also because it takes into account the most unfavorable condition of a splitting failure at long embedment. So the conclusion is that there is no strong link between these two values. In the framework of this European assessment document issued by the EOTA in Europe and the Eurocode 2 Part 1 design bond stress value. And this is a good news, because it means that a system qualified according to this document can be safely used also in combination with other international reinforced concrete design standards, such as, for instance, the Indian standard 456. And here it's also shown exemplary for the case of basic bond strength, comparing the value of Eurocode 2 with the Indian standard 456. On the left-hand side, there are the analytical or tabulated values of these two standards, and on the right-hand side, one can see that at the value of the Indian standard 456 valid for the limit state design are quite similar to the value of Eurocode 2. And while for permissible stresses, the values are obviously significantly lower. What is also important to be reminded that obviously we need also to talk about the same type of reinforced deformed bars, which should comply with the requirements of Eurocode 2 Part 1 Annex C, which is the case in the case of Indian standard 1786. Obviously, all these provisions are not valid for the use of plain round bars, which is anyhow something which is becoming more and more rare nowadays. And then if we look, for instance, in the design of an anchorage, again, we can compare the different standards. Similar comparison could be done also in the case of design of lap joints with some minor differences. So from what regards the Eurocode 2 design, we typically have a so-called required anchorage length, which is calculated with a formula that we all know. And there are some reduction factors which are called alpha 1 up to alpha 5, take into account for different beneficial or also detrimental factors like the shape of the bars, the concrete cover, transverse reinforcement, welding of reinforcement, or transfer pressure or tension that may act orthogonal to the bar. And the India standard 456 has a probably slightly simpler approach, but following the same philosophy, where, for instance, bends and hooks may bring to shorter anchorage lengths. Obviously, bends and hooks cannot be achieved with this technology of post-install reinforcing bar, and therefore it's important to ensure that the local code used in design is allowing also the use of straight anchorages, which is the case of the IS 456. And then going ahead, I would like just to mention briefly about some particular aspects of the qualification and design of post-installer reavers under special loading conditions, which are seismic loading, fire exposure, and extended service life. And it's needless to mention why these special loading cases need to be considered in a separate way, and the static assessment, as shown in the earlier slides, cannot be sufficient, because obviously the suitability of the mortars for such condition need to be proven. So starting from the assessment for seismic action, again, we need to look into the two main failure modes of a post-install reinforcing bar to make sure that its behavior is not worse than the behavior of a casting bar. So in the case of pull-out, the bond strength degradation, which is a natural behavior when we start cycling a load. What is represented here, it's an alternating cycle tension load of a bar. And of course, with increasing number of cycles, the bond strength decreases. And we want to make sure that this behavior is not worse than the behavior of a casting bar, which is in many cases has some advantages because of the beneficial effect of the ribs. And for near edge conditions, we need to check that in the case of splitting failure, the energy dissipation is not poorer than the energy dissipation of a casting bar. If this is the case, then the product under investigation can be used only with increased concrete cover, which is obviously a strong limitation, but for sake of safety, of course, we need to consider it. And then I would like to talk about a topic which is gaining the interest of authorities and professionals because of this relevance on very important and strategic structure like infrastructures, which is the working life. So what I've been talking until now is typically valid considering a standard working life of 50 years. So what do we need to ensure for a product to be suitable for extended working life, which is typically 100 years at least under the assessment and qualification provision established by the author. We need to ensure that all the properties which are time cycle dependent are also valid for a longer period of time. And based on the theoretical and technical background of all type of tests that need to be conducted to qualify a system, the creep behavior, which is checked with appropriate so-called sustained load test, is usually tied to a working life of 50 years, and therefore must be reconsidered in the case of a 100 years service life. And where do we need this? As I already said, we need for particularly important buildings what in Eurocode 0 are the so-called monumental buildings or infrastructure such as bridges or tunnels. And also several national standards have specific requirements in these regards, or alternative, maybe simply the owner of a structure which would like to make sure that his investment in term to build for a building operation is considering an extended service life. And now I've been talking a little bit with European perspective, but this can be easily found also in the Indian scenario. So we have also in India, there are codes like the IS 8875 part 3, when considering a different action structure, considers also a different design life of the structure up to 100 years, and which is something that is considered nowadays in the in approvals of premium products. However, we might have also stronger requirements. A common requirement is 120 years, which is linked to the British national annex of Eurocode 0, and it's quite common in all those countries which have still a stronger relationship, a stronger link to the British standard, which is, for instance, the case in India. It might happen. And this is a topic which is not currently handled by approval processes, but might be handled in specific expert reports, which are reports written by experts in order to assess this performance of extended service life for specific products. For instance, here is the example of the report for our epoxy R500 V3, written by Professor Konrad Bergmeister, that for who of you don't know him, he's just to present him in a few words, is the technical director of the currently largest, longest tunnel project in the world, which is New Brenner Tunnel between Italy and Germany through Austria. And another important aspect, because when we design a reinforced concrete structure, we need to deal with also the unfortunate event of a fire, is the behavior under fire exposure. And this is for most of post-install river system, being the chemical mortar typically of polymeric basic with quite low percentage of inorganic materials, which are usually less sensitive to fire. The performance is, in terms of bond strength, is significantly reduced with increasing temperature. So on the left-hand side, you see an example of how the fire exposure performance of the system is assessed in Europe, conducting pull-out tests at different temperature level, and one can define a so-called fire curve. When you see that, when we come a temperature between 200 and 300 degrees, the performance is quite reduced. And once we have defined this type of curve with an approval process, and this type of curve is typically part of the European technical assessment of the ETA, then this data can be used to conduct a design according, for instance, to the Eurocode 2 Part 1, Part 2. And knowing the type of connection that one is considered, which might have a non-constant temperature along the embedment, which is the case of this left-hand sketch, or a constant type temperature, like on the right hand side, one can define a temperature profile according to the relevant standard, and via a numerical integration then can assess the pull-out resistance of the post-install rebar system under such condition of boundary condition, and obviously also of time of the fire exposure. So after this very quick overview of what was going on in the last 20 years in terms of this design and qualification of post-install rebar system in Europe, I would like to move a little bit further and look into the applications with post-install reinforcing bar, and also explain why it's important and useful to look in such applications. It is something already well known since the beginning of 2000 that actually post-install rebar can perform significantly better than casting bar, and this is shown based on confined pull-out test with large and small cover conducted at the beginning of 2000. Obviously, since that time, the technology of the chemistry of this chemical mortar, this additive system, has improved significantly. We have performance which are twice as high as shown in this diagram. But we are also aware that we cannot always count on this better performance. And this is an example of a test which is a mandatory test according to an assessment procedure established in the United States, which is based on a pull-out test of a casting bar, and side by side a post-installer bar in a prismatic element with minimum concrete cover and a long embedment of 32 diameter. And what we've learned from this type of test, that under this type of boundary condition, the difference in performance between casting bar and post-installment bar is basically negligible. And this is something that we need to keep in mind, that, well, maybe under certain conditions we can utilize higher bond strength of post-installer rebar versus casting bar, but not under any type of condition. And for this reason, we need to look in what are the type of application that we want to address with this technology. And these are three families of application that we typically consider. So on the left hand side, you see so-called lap splice, lap joints. So when we have an existing element, here is shown in this 2D sketch as it could be a slab or a beam, but could be also turned by 90 degrees and be a column or a wall that need to be extended. And we already have some longitudinal reinforcement in the existing element, and installing close to it post-install reinforcing bar, we can ensure a continuous transfer of forces via so-called non-contact splices. If we don't have this type of situation, but we might have a situation that we need to design a so-called end anchorage, and which is shown in the sketch in the middle, where we typically intersect a new element to an existing structure element. And then we have a third one, a third categories where we are also talking about end anchorages, but the biggest difference to the standard end anchorage situation is that here the main type of action between the new and the existing element is not a bending moment anymore, which is translating into tension and compression in the zone of the member, but it's mainly a shear force. And this is a technology which is commonly used in many strengthening and retrofitting applications. And I would like to spend a few words on these three group of applications. So talking about lap splice, as you can imagine, it's quite difficult, if not impossible, in most of the cases to utilize higher bond strength of a post-installer rebar versus a casting bar, because this type of connection can be compared to a chain. And in a chain, obviously, if there is one ring stronger than the other, it doesn't matter, because the weakest link of the chain will break first. However, there are other aspects that we need to take into account very carefully. It's, for instance, the displacement behavior. Is the displacement behavior of the casting and post-installer rebar the same, or is potentially the post-installer rebar system weaker or softer, which makes more displacement? And this could be a downside risk because of endangering the serviceability via opening of large cracks, and potential also bring it to problem in transferring the shear in the interface. And in order to investigate more in depth this topic, we have started some university cooperation. And here I would like to show you a short video about a lap splice simulated with a so-called direct tension test. And we have, in this particular specimen, we had that the top bar were post-installed, while the bottom bar were cast in. And using technology which is derived from the principle of photogrammetry, we were looking at the displacement behavior of this system. Now, I hope that you can see my video, which is now starting. You can follow the loading on the right-hand side. And now, if I have a short break, you can see that the top bars, which are post-installed, have displacement around 0.1 millimeter, while the bottom bars, which are the casting bars, they're already at 0.25 millimeter. And now, going ahead and getting closer to the ultimate resistance, you see that the difference is becoming significant, right? The displacement of casting bar is almost twice the displacement of the post-installer rebars, which is a good indication that the system used appears to be suitable for this type of connection. This might not be the case for all systems. And then, approaching the ultimate resistance, it was too fast. As expected, what happened that the failure started from the side of the casting bar being those weaker. So confirming basically what we were showing, but I think it's important to have also this type of experimental confirmations. And now I would like to go to the second family of application, which is the anchorages in structural joint. And here we have, I think that all these three sketches that you see here are familiar to you. And the first on the left-hand side is a typical reinforced concrete connection. Could be a column to foundation design according to Eurocode 2, where the ending of the longitudinal starter bars is ending with bent. It could be bent in or bent out of the joint, but this depends on the type of application, but this is a quite standard solution. On the other hand, if we look at steel connection, if this column is not of reinforced concrete anymore, but made of steel, then we can use, according to the provision of Eurocode 3, straight anchorages, and using the anchor theory to connect this steel column to the foundation slab. Now, if we have the same type of connection, again with reinforced concrete, but with post-installer bar, as you can see, we have a hybrid situation between these two. So you see that the provision of Eurocode 2 and Eurocode 3, and maybe in India the situation is also not that different. This design provision are quite different from each other. And now with this technology, we are in a situation that we need to find a meaningful, technically sound and safe way in between. And to this end, I would like to show you two short videos based on tests conducted in cooperation of the University of Stuttgart, which have been recently published. These are connection with a column to foundation with cast-in and post-install reinforcing bar. Both are straight bars for comparability. There are 20 millimeter diameter bars anchored at 350 millimeter embedment. And I will show with this video the behavior of the cast-in bar. As expected, we have a flexural behavior of the column in the first part of the test. As you see also from the hysteretic behavior, that's the behavior in this phase is still quite linear. Then after a while, I will speed up a little bit. We will start getting some damage in the foundation, but the behavior, I think it's still quite satisfying. But then after a while, you see that the behavior is getting more and more pinched, and the damage in the foundation is increasing significantly up to a certain point where we really have a swallow formation of a concrete breakout, indicating that the bars are getting pulled out. And now let's see what happened with the same type of test using a post-installed reinforcing bar. Again, in the first phase of the test, you see a quite similar behavior, flexural deformation of the column, which is highlighted by the formation of flexural cracks, and advancing with the test, increasing the level of deformation. We also get some limited damage in the foundation. Now I'll speed up a little bit. And here you see exactly what any seismic engineer would like to see from the behavior of a column, a very nice ductile behavior of this element. Of course, in the end, there is some degradation due to the crashing and spalling of the cover, but here we are at a drift level, which is well beyond what is typically required for in the case of a seismic design. And this is, I think it's important because show that, well, there are situations where we can really utilize the superior performance of a post-install rebar system. And at last, I would like to talk a little bit about so-called shear friction application, which, as said, are commonly used in a retrofitting operation for both building construction as well as civil constructions. And currently in Europe, in order to design the shear friction interface between concretes cast at different times, we have the provision of section 6.2.5 of Eurocode 2, which, however, allow only the anchorage length calculated as per casting bar. And obviously, in order to fully anchor these dowel bars, then we need very long embedments, meaning very thick concrete member, which is in many cases something which is not feasible. And in order to overcome this problem, the European Organization of Technical Assessment has recently issued a so-called Technical Report 66, which allowed to consider the real bond strengths of the anchor system to be taken into account, and this enabled to provide solution also in the case of shorter anchorage, because maybe the new layer of concrete is typically not having such thickness that would be required by the standard Eurocode 2 equation. And this is an example. If we need to anchor fully anchored dowels in a C2025 concrete using the traditional Eurocode 2 design, we would need more than 30 diameter embedment, which will be almost half a meter for a diameter 16, and only less than 10 diameter in the case of this new design method. And what I've been showing until now is something very new, and is something which is coming more and more. And what I'm showing here is just some recently published a document of European Organization of Technical Assessment, both to qualify product for special application like shear friction interfaces and design of the end anchorage in rigid nodes, and also the respective guidelines, which are called technical reports in the wording of EOD. So concluding, what I've been presenting today is the way of a little bit something about the way of qualifying and designing post-installer rebars that can be used in lieu of casting bars when a new member is cast and connected to an existing structure. And as you have seen, the qualification and use of this system is not limited to static loads, but also fire exposure, seismic loading, extended working life can be considered, but only if the specifically qualified system is used. And after that, we have been looking a little bit in the newest advancement in this technology, and something which will be definitely developed further in the future, which is a performance-based application-based use of post-installer reinforcing bar in order to utilize the better performance of post-installer rebar system under specific condition. And these advancements of which are thanks to these extensive research activities are paving the way for application-based use of post-installer rebar system, which will be allowing more economical, feasible, and at the same time safe use of this technology. And with this, I would like to thank you for your kind attention, and I will be happy to answer to your question at the end of the session. Thanks a lot.
Sure. Thank you, Dr. Janicio, for this insightful session. It indeed was very knowledgeable to learn about post-installed rebars. I would now like to take this opportunity and invite our second panelist for the day, Mr. Amol Singh. He will be talking about post-installed anchoring. Before I hand it over to Mr. Singh, let me introduce him to you. He currently works at KT Asia Pacific and is responsible for providing technical consultation for structural fastening applications to construction professionals across India, Southeast Asia, Australia, and New Zealand. Mr. Singh previously worked as a consulting structural engineer after having attained his master's in structural engineering from Cardiff University in the United Kingdom. I now hand it over to Mr. Ramon Singh to take it forward.
Thank you very much, Karan, for the introduction. A very good afternoon to all our esteemed members from the Institute of Engineers. I hope you're all in good health during this time. As Karan said, I will be providing you with a brief overview on the selection, design, and installation of post-install fasteners that connect new steel elements to existing concrete ones. My colleague, Dr. Janicio, covered the connection of new concrete elements to existing ones. I'll be doing it, but just we switch the materials to steel. Okay, so in preparation for this webinar, we collected over the years a few questions on post-install fasteners commonly asked by practicing engineers and designers. Members of our audience may have had similar questions in the past when dealing with these, and as I read them out, these questions should jog your memory to times when you had these situations. So, firstly, why do I need fasteners? Where do we see these connections in the industry? What are the different forms of them, and how do they work? How do they fail, and how can I design them? Is there a uniform design method? And what data do I need to design the connection? How are they installed? And does it even matter in the first place? And how do specifications work? And why do specifications matter? And can I replace one anchor with another? And I will cap off with a couple of further resources, and that we'll take forward afterwards. All right, so to get everyone warmed up on the topic at hand, think for a second, what purpose does an anchor solve? And why do you need it? So while you're thinking of that, quite simply, we're trying to connect two objects together. So if you look around your house right now, you'll find fasteners connecting various objects such as shelves, television screens, heating vessels, fans, air conditioners, and other interior architectural features. And they'll be connected to walls, floor, beams, columns, anything that they can find. Let's call these objects non-structural components. Now, if you extrapolate this on a slightly larger scale, we're connecting larger elements that participate in ensuring structural integrity. And these are called structural components. An example of this is a steel section to concrete. Hence, we're no longer looking at fasteners in isolation. Rather, we're looking at it holistically as a connection that has an impact on either the structural integrity or the safety of those inhabiting the building. The industry gives these connections many names, such as anchorages, fastenings, fixings, but remember, they all consist of fasteners, which are always more than one if you're looking at a structural component, the base plate itself, and the base material, which can be concrete, masonry brick, or steel, and the attachment itself, so the metal or the steel beam or steel column, whatever you're connecting to that base plate. So think of this connection as one, and then we can move on from here. So while the possibilities are endless, today our session will solely focus on steel to concrete connections, since they form the bulk of the connections we see in the industry. Okay, so now where all would you see these fastenings of steel to concrete elements? So you might see them in portal frames, such as in warehouses, where you might want to connect the steel column to a concrete pedestal. You'll also see them if you're constructing a steel framed multi-story building to a concrete foundation, such as a raft. You'll also see them in steel jacketing, being used in steel jacketing, where you might want to strengthen an existing concrete element. They'll also be in corbel beams. So these are used in industrial plants where you might want to run a conveyor belt and other forms of machinery on that section. And of course, you have the ubiquitous steel beam, which is used to extend concrete floors and concrete buildings in general. These connections would be subject to the largest static and dynamic actions over the lifetime of the structure. And here, fastenings are the point through which bending and shear resulting from all the different actions is transferred from the steel element to the concrete base, and whether that base be a foundation, column, wall, anything. The idea is to ensure that this connection acts in unison with the rest of the structure. So that's what we're looking for here. You'll find this also that fasteners are used to fix certain curtain walls and other facade features to the main structure, and they also form a key part of the structure, not just transferring their own loads and the loads of the subframe, but also the wind and any seismic actions that are acting on it onto the main structure. So in essence, the concept remains exactly the same. What differs is what you're attaching to that base plate. We also see fasteners being used in fixing services, M&E services, to the soffits of beams and slabs. We also see heavy-duty fasteners being used to fix industrial equipment and machines subject to a lot of vibratory loads, and these also use plenty of post-install fasteners. Okay, so now that we've identified the component we need to connect our base plate to the concrete element, we must now choose the anchor. So of course, it makes little sense to use the same anchor to connect the structural and the non-structural members. So you can't, there's not one size fits all. An analogy would be that would be using an M24 anchor to fix your ceiling fan. Of course, it's definitely possible, but it's quite unnecessary and overkill for the task. So before we choose our anchor, we must be aware where in the construction sequence we are. Okay, so that's quite important. So for a structure that's still under design, it's quite natural to look at cast in place installation, as this would be the most suitable option if positional accuracy can be assured during the casting of the concrete. And if this cannot be assured, then, well, you still have post-install options available. So cast-in fastenings come in 3 variants. You can have individual bolts. You can have a group of 4 or 6 or 8 attached to a base plate, pre-attached as it comes on site. Or you could have what we call an anchor channel with at least 2 anchor legs, and that can be also used as well. On the other hand, if the position of the cast in fixing was moved during the installation, so if you had the bolt which was dislocated as you ran the vibration, someone knocked it over, or let's say, this happens quite a lot, that the contractor forgot to put the bolts entirely, or if we're considering an existing structure, then post-install fastenings become the only option over there. Okay, so when choosing post-install systems, we have the option of doing drilled fastening or direct fastening. While direct installation systems fire a nail on the fixture using a powder or gas actuated tool, post-install drill systems require drilling a borehole prior to installation. Since drilled systems can withstand much larger forces, we will focus on these for the remaining session. Okay, so looking at all the drill fasteners in the market can be a very daunting task. I was in a similar situation as many of you before joining Hilti, so I really sympathize. But if we're looking for to connect our new steel component, or beam or column, to an existing concrete, for example, it makes the selection process a little bit easier. We can now narrow down to the different mechanical and chemical options best suited for the job. And at this point, I'd like you to imagine that you have the same task at hand. Which anchor would you select from what you can see on the screen? I mean, there's a lot of choice here, right? Of course, this one is completely out because it's only for masonry. However, all of these apply. The other 2 chemical options apply. So, it still doesn't really narrow it down too much. It just weeds out one of based on the base material. So that's a good place to start. Okay. So to select the most suitable anchor for a fixing, we also need to understand how they work. So despite the many differences in quality and performance and application coverage, all post-install anchor technologies have a common ground. And that common ground is the way they transfer the load into the concrete base material. And this is based on one or more of the following principles that we'll cover. So the first one here is friction. Okay, so in friction, you have a tensile load that acts on the anchor, and this has to be balanced by the forces of friction and the expansion forces lateral to that to generate the sufficient holding power. And this is only done by applying a certain amount of torque or additional force or displacement to this. Keying is when an interlock occurs by undercutting the concrete. So as you can see, this little wedge over here that's called the undercut, and this creates an interlock with the fixing. And here the tensile load is in equilibrium with the supporting forces acting on the base material. So the way you can do this is by a special drill, or fasteners come equipped with cutting edges, or you can use concrete screws, which do the same thing. We look at further examples of this in the upcoming slides. And lastly, of course, we have the famous adhesive bond, which is produced between the anchor rod and the borehole, and the adhesive basically transfers the tensile load into the concrete via a bond stress. So from a combination of working principles, some anchors may use bonding or friction, bonding or keying. So the idea is the resistance derives from these working principles. Okay, so now that we know how these fasteners will work, it's a matter of understanding which fasteners are associated with the working principle we talked about. So for example, metal expansion fasteners work mostly through friction after being inserted into the borehole, and they need to be activated by displacement or torque. Otherwise, they will not work and you can pull them out easily. So displacement controlled expansion anchors transfer the load onto the base material using a special tool, which you can see over here, this red one, which hammers a little piece inside this anchor. Okay, so that's how that displacement controlled expansion anchors work. torque control expansion anchors, as the name suggests, require a specific value of torque to be applied on the nut, and this expands the sleeves at the bottom, and therefore you can hold the fastener in place with friction. So let's have a look at that with a video, which you'll be able to see. As you can see, the cone pulls into the sleeves and expands the fastening into the base material. So if you weren't able to see that, I'll play it again for you. Again, so we'll pause it at the right time. There we go. All right. Oops. Okay, so you get the picture. So basically, these sleeves expand and transfer the load into the concrete. All right. So with the other two types of mechanical fasteners that are undercut and screw, key plays an important role. So the undercut variety, which you can see, that's the classic one we spoke about. Here we create a dent in the concrete through either a special drill before we install the anchor, or by the anchor itself. So let's have a look at that. Either way, you will see that these in this, the sleeves over here, which you can see, have a cutting edge, and as they're pushed in with the tool, they create a cut in the concrete and slide over the sleeve. Okay, and this is how you get that undercut, and this is quite a strong connection. The idea is the same with screw fasteners, but on a smaller scale, with more numerous dents created by the screw thread. Let's have a look at that. So, and we use an impact wrench to drive the screw in. So as the screw is driven in, you can see that the leading edge of the anchor, the one that's the deeper inside, is having these little cuts, or let's say teeth, as they cut into the concrete. And this is how, on a smaller scale, you can see how it's being held in place. Okay, so on a very small scale, we do this. Okay, so that's how we go about doing that. All right, so last on our list of mechanical fasteners is the plastic variety. And these rely on the same principles of friction and keying, but it depends on which base material you're installing them in. So in concrete, the plastic sleeve over here expands and pushes against the borehole when the rod is screwed in, thereby increasing the friction force when pulled. When you install it on hollow block masonry, the sleeve expands and creates the specific shape that you can see on the right side of your screen when the rod is screwed in, and therefore this creates a little key when it's pulled. I mean, think of it like you're inserting your key inside your lock, twisting it halfway and then trying to pull it out. That's essentially the action that's happening with keying. All right, so as we move on to chemical anchors, the adhesion of the polymer and its interaction with the concrete plays a vital role. So in addition to friction and keying. So standard bonding functions when the mortar adheres to the concrete and to the rod, transferring the force applied on the rod to the concrete. You can also see a bit of micro keying happening between the threads of the threaded rod and the mortar itself. Bonding friction occurs when you have adhesion and friction. So this depends on the shape of the rod as it's pressed against the mortar. So here you can see the tapered wedges. If I just zoom in slightly, you'll be able to see these tapered wedges that push against the mortar, thereby creating the frictional force over here. And lastly, we see again keying occurring when the mortar hardens against the mesh sleeve, and the shape creates a mechanical interlock with the holes in the masonry block. The use of the mesh sleeve also prevents uncontrolled spillage in the voids within the block itself. Okay, so just to recap at this point, using our example of a base plate on a concrete column, we've understood why we need post-install fasteners, and we've understood that there are different types for different base materials and that they function through different mechanisms. So as an engineer, I would now need to know how these fasteners and thus this connection can potentially fail. Okay, so let's dive into that. So to do that first, we need to understand how fasteners fail in tension and shear, And this exercise is not very different to how we would check the capacity of a connection in a normal cast-in scenario, where we check all possible means of failures and then select the worst case scenario. The first theoretical concept we need to understand over here is that concrete can fail in tension. Yes, you heard that correctly. In reinforced concrete design, we do not consider the concrete tensile capacity. But as you'll see here, we need to consider it for anchorages. Okay, but first let's cover the steel failure. Here, the weakest part of the connection is represented by the rod. The failure corresponds to a tensile breakout of a steel piece, similar to what you would find in a laboratory testing condition where necking occurs prior to failure. Very common. This is something we might desire. We don't want to damage the concrete, and so we want to use a ductile mechanism for failure. Now as we move to concrete cone, and this is quite important, is that after reaching its tensile capacity, a cone shape starts to form, starting from the bottom embedded part of the anchor. And here the failure is governed by the crack growth in the concrete, and this failure mode is the most common one. You'll be surprised to hear, and some of you might not be surprised, because concrete cannot resist high tensile loads. So thus, this by default also becomes our key failure mode to consider. Pullout is split into two, depending on whether you're using a mechanical fastener or a chemical fastener. The idea is still the same. You have the anchor being pulled out completely, with sometimes damaging the surrounding area of concrete over here. So for mechanical fasteners, the way this happens is that there's a complete loss of frictional or keying forces and that hold the anchor in place. So this is lost. So for chemical fasteners, this is known as bond failure. Well, the name is quite self-explanatory. The bond fails and the rod is pulled out. And the last one you have for tension is the splitting failure, which is characterized when you have a splitting crack that divides the base material into two. This normally happens when your existing concrete thickness is too small and you drive the anchor in way too deep. Okay, so this can happen as well. So another way you can have splitting is if you're too close to the edge, you can have cracks that form from the anchor to the edge. Another way you can have it, if you're not close to the edge, if you're in the middle of, let's say, a foundation, if you place the two anchors close together, there might be a crack between, and then a crack might form between the two of them. All right, so let's move on to shear. And we also have steel failure in shear. And this can happen when the rod shears off after developing large deformations. And this is similar to the steel failure in tension, but occurs roughly at half the tensile capacity. So next is we have pry-out. This is a concrete failure, which is very similar to trying to, when you're looking for your spoon, you dig it into ice cream, you try to scoop up that ice cream. That's essentially what pry-out is. Okay, and we're applying a shear force in the direction opposite to the failure. So failure occurs here. So as you can, if you follow my cursor, let me just use the laser pointer here. Okay, so if you can see this little shear force acting on the anchor, as the anchor pushes away, it starts to displace this bit of concrete over here. Okay, that's how pry-out occurs. Concrete edge, as the name suggests, is the fracture area, the failure surface close to the edge, and this occurs in the same direction as the applied shear force. So as you apply the shear force from right to left, the concrete on the left side of the anchor will displace entirely and might spall. The last bit we have is a combined failure mechanism. So all it does is basically takes the worst case of tension and shear and sums it up into an interaction curve, similar to what you might see in a von Mises stress strain diagram. So that's what you can see in interaction on the two axes. So as you can probably tell, a ductile failure cannot be guaranteed for post-install fasteners. By the way, this is also the same for cast-in fasteners as well. Because we are considering the tensile capacity of concrete, which isn't the highest when you compare it to steel or an epoxy mortar. So just bear that in mind as you go about designing these connections. All right, so let's have a look at how this failure might happen, how steel failure might happen in tension. This will not be very surprising to you. It's a very sudden, violent break, and it will just, you'll get a little bit of advance notice beforehand. Okay, let's have a look at concrete cone failure. So what you'll see is the concrete cone developing and there. So I've just paused the video. Don't worry, your screen hasn't frozen. Over here, as you can see, this concrete cone starts to form and it's already failed. Okay, so that's what we're looking at over here. All right, lastly, let's look at a pull-out failure. So over here, we have a mechanical anchor that's positioned in concrete. As you can see, I've paused the video again. You'll be able to see a few cracks developing over here, and that's essentially what pull-out is. So basically the anchor has pulled out and it's brought the concrete along with it. Okay, so just like a steel or concrete member, there are several parameters that influence the performance of post-install fasteners. And these include the environmental conditions, the load duration, the type of load, most importantly, the concrete type or the base material, the orientation, the embedment depth of the anchor, the diameter, and many more. Let's take, for example, the depth of the anchor. So this is a key parameter that influences the resistance to tensile and steel failures. Okay, so ideally we would want to install the anchor as deep as possible to maximize the resistance to concrete cone or bond failure in tension. Right, so these two we want to maximize. But on the other hand, going too deep can also cause the concrete to split. It may even start reducing our cone capacities, because as you go deeper, the cones tend to interact with each other, and therefore you get this void area where you have no resistance whatsoever. Okay, so that can cause the concrete to split as well. Now, for steel failure, should we increase the depth? Well, the answer, it has no impact. So because the steel failure is governed by the cross section of the rod or the anchor in this case, and its yield strength. So there's no point in going deep for a steel failure, to guard against the steel failure, sorry. For mechanical anchors, it's also very interesting to note that going deeper will not give you a lot of benefit in terms of pullout, because if you take an expansion anchor, what might happen is that the sleeves are at the end. So the pullout failure will happen irrespective of the depth. Okay? So it's not always that deeper is better, larger diameters are better. Sometimes you have to balance these things. And the way we balance it is using limit state design. So as you know, the weakest resistance of the failure becomes the design resistance. And this governs the performance under the specific load scenario we're looking at. So just as you design reinforced concrete and steel elements, the entire anchor design theory is also based on limit state. And let's take our example here. We also have, just by the way, partial safety factors for loads as well as for resistances. Let's go back to our example, which we used for connecting a steel base plate to a concrete column. So let's say that we are subjecting this this beam where the boundary conditions are simply supported, so we only have 100 kilonewtons of pure shear. So we need at least 100 kilonewtons of design resistance to prevent failure. Now, if this in shear, we remember we have three failure modes, right? So we have the steel. So let's say, for example, it's 200 kilonewtons in steel, 110 in concrete edge breakout, and 120 in terms of pry out. So it's quite natural that 110 kilonewtons will be the governing resistance over here, right? So that's going to be the lowest. So ideally what we want is a very close margin between the design loads and the resistance. So this will lead to an optimized design. Now, the overarching design principles that we consider for a fastening also remain the same. We've covered the ultimate limit state over here, where basically the fastener must sustain all loads during execution and use. the serviceability limit state, where the fastener shall not deform beyond certain limits. And this limit has then an impact on your, let's say, steel beam or column. So if we're considering L by 250 or L by 350 deflection limits, that's what goes in here. And of course, the durability, whereas the fastener must remain fit for use throughout the structure's lifetime. So that might be 50 years, that might be 100 years, might be even more. So that's a key thing to account for as well. So at this point, you're probably wondering that yes, we need some sort of design, but you also might be aware that the Indian standards contain no guidance on this, no provisions to help us design. Whether they are cast-in anchors or post-install anchors, we just don't have that approach at the moment. And since design guidance is scarce, the industry adopts very novel approaches for this design. The first one is the famous manufacturer's load table, which you can find in the catalog. So what this contains is a bunch of load values, which are indicative, and they do not cover all design scenarios. What I would request is that you take that catalog and just put it aside, and it's nice to look at, great, but really it's worthless when you're trying to design. Now, the next thing you can consider is increasing the design load or safety factor. But this doesn't really make much sense, as you're then overestimating the loads that will happen. And that will lead to an unoptimized design. And in some cases, the solution that you're trying to fit into that design may not even work. Number three, you could apply additional reduction factors to the anchor's capacity. So if the anchor can resist 111 kilonewtons, you might reduce that by half as an arbitrary value. Fine, it gives you a peace of mind, but is it really, will it really work in the scenario? Maybe, maybe not, we don't know. And lastly, you could also consider using just a tested or an approved anchor and think that this might give you some security and peace of mind. Well, that would be a start. However, much of the industry resorts to turning a blind eye and pinning it on the manufacturer to guarantee that the anchor will work. Well, the manufacturer cannot become the engineer and design for you. The manufacturer doesn't know what loads are coming on your structure and what's coming on your base plate. A lot of them might not be even knowing what level of analysis you've undertaken. So this responsibility of design rests with those who are experts at design. And sometimes these novel approaches can have some unintended and devastating consequences if the background is not understood very well. There are many failures we can point to, but here's a selection of three ranging from Boston to Shanghai and back to Texas again. Each of them had their own causes, and there are plenty of reports for that. The one in Boston is particularly important because for the first time it highlighted the effect of creep in chemical fasteners. And this resulted in huge changes to the testing regime of chemical fasteners. Now, I mentioned that these are not all due to design errors. Of course, installation plays a major part in that as well. And we have to link these two concepts tightly, design and installation. We'll come to installation a little bit later. What's crucial is that as engineers, we cannot jeopardize the lives of people. And often all it takes is a tiny little anchor to separate the lion from its snack. So to avoid becoming the lion's snack, we first need to appreciate that this connection design is a real issue. So in relation to our example of a base plate connected to a concrete column, that 100 kilonewton in shear example, let's ask ourselves this question. Does failure of this connection risk structural collapse? Does failure result in the injury of the building's occupants? If the question of either of these two, if the answer to either of these two questions is yes, then the connection must be designed. It's as simple as that. Just these two questions will let you know. Okay. But is that what the industry does? Well, I'll be very honest. We see some very interesting examples of design. We've seen them in the past few slides. This happens primarily because of a lack of appreciation that this is a real issue and you cannot design out of a manufacturer's catalog. So like I said before, please park that catalog aside. Maybe nice, colorful thing to look at, but completely useless in design. And through specifications, fastenings often are included in the contractor or subcontractor scope of work who might not appreciate the importance of design. They wish to get the job done fast, they wish to get the job done cheaply, so they might not appreciate what it means to the overall construction. Clients and their advisors or project management teams who delegate the task of fixing these do so without engaging in real design. So ultimately, it becomes a question of who's responsible, right? But that's for the industry to resolve. So I hope so at this stage we can agree that we need the design. So the first step we also need to do is establish some boundary conditions or some parameters that are specific to that connection. So using our example of a base plate on an existing concrete column, we need to establish the requirements based on the overall project needs. So does the connection need seismic performance? Do we know the state of the existing concrete? What levels of corrosion protection do we need to offer? Is the connection going to be subject to the elements? What are the service life requirements? 50, 100 years, what else do we need in terms of durability? What is the fire rating needed if it's indoors? Is it 2 hours, 3 hours, 4 hours, who knows? And does the building owner or client need a green building or LEED certificate? That might be a question as well. But most importantly, can the existing concrete resist the additional loads imposed by this base plate? So that also is a crucial part to check. And maybe there are other things as well, who knows? So these are just a few examples, they're not limiting. We can only establish these as you move on to design. So if there is no Indian standard, how do we actually design? So luckily there are a couple of international standards that contain detailed design provisions. The state of the art today is the Eurocode, which can be used in the absence of any local standards. What we are looking at specifically today is Eurocode 3 for the steel element, and Eurocode 2 for the concrete element. And the way you connect these two is using post-installed anchors to Eurocode 2 part 4. That's the crucial bit over here. So does that mean you need to design the entire structure to the European standards? Well, not necessarily, but an understanding of the structure makes sure that we're not omitting anything unintentionally. We can still design our steel elements to IES 800, our concrete to IES 456, and still use the state-of-the-art Eurocode 2 Part 4 to design the connection itself. And we use this until the Bureau of Indian Standards is able to plug this gap with a suitable Indian standard. Right, so just from the cover page of this standard, what can we see? The scope is that we're talking about fastenings into concrete. That means the fixture, that means the base plate, which is the base plate, and that means the anchor itself. So that's what we call as a fastening. Okay, so again, going back to the beginning of the presentation, I mentioned we're looking at the connection, and in this case, the fastening is the connection. Okay, and the level of importance the fastening design has is now the same as the concrete structure itself. That's the overall importance that it's been given to fastening design. So contained within the standard, the engineer will find design formulas to calculate the failure modes we covered earlier, such as the ones in tension and in shear. Under the standard now, we can also design our base plate onto the column for different failure modes for different load combinations, so that they may involve static, seismic, fire, fatigue. These are the 4 ones covered by Eurocode 2.4, and they will suffice most of your requirements. But to do this, we need data specific to the fastener, and this comes from what we call European technical assessments, which are specific to the fasteners, or ETAs. You would have seen ETAs being mentioned by Dr. Janicio. That's for connecting concrete to concrete. Here we're looking at ETAs for fasteners connecting steel to concrete members. So remember, there's 2 different ETAs we're talking about on the two different systems. Okay, so each fastener will have its own ETA. That's proof of its being tested. So these ETAs are documents specific to the fastener and that are published after rigorous testing of the fastener by specific independent and third-party assessment bodies that are set up specifically to deal with the testing demands of fastening. So to undertake this testing, we also need a uniform testing criteria to ensure that there's a level playing field for all manufacturers and that there's transparency to everyone in the industry on how these fasteners are assessed. And these are known as European assessment documents. Okay, so a manufacturer cannot claim performance that differs to that stated in the ETA unless they apply for testing. That part is super key to understand. This part is being tested. So at this point, we know that there are different fasteners and they require testing and assessment to qualify for a designated performance level. So let's use the example of 3 mechanical fasteners that you can see illustrated on your screen and apply them to the base plate, which we wish to connect in concrete under seismic conditions. Now, I'd like you to take about 10 seconds or less maybe to think, just take a guess, which one of the 3 will be approved for seismic. And after you've thought of that, I would want you to write down in the chat box one of 3 colors, black, blue, or red. Okay, all fasteners are from the same manufacturer. You can start doing this now. All fasteners are from the same manufacturer, but only one is assessed for static and seismic, one is assessed for static only, and one is not tested at all. So I am waiting for your responses in the chat window. Just type in a color, black, blue, or red. Which one do you think works in seismic conditions? I would request if our moderator, Karan, if you can see the responses, you can tell me the most common one.
Yeah, we are getting a lot of responses, Ramon. A lot of the responses say red. Some also say blue.
Okay, thank you. So keep those entries coming in. If you guessed red, well, you guessed correct. But even if you weren't able to guess the right color, that's no problem, because without knowing, without an ETA, you can't visually tell which one would perform. There is no way you could. So you need testing to help you do that, right? And that's where the ETA comes into picture. Okay, so the crucial thing to realize is that fasteners are not standardized construction products such as reinforcement steel, J-bolts, L-bolts, studs, but they still need certain regulation under a harmonized and unified assessment criteria, which is the EAD. And the material components that make up these anchors must conform to internationally recognized standards. Manufacturers, however, are not bound to make the exact same type of fastener, and this is undertaken specifically to ensure that the sector remains open to innovation. Think of it like the automotive sector, for example. I mean, the point of any car is to safely transport you from point A to B, much like the purpose of any fastener is to connect material A to B. But some vehicles make your ride a bit more comfortable. They go over potholes without giving you a sore back, give you better mileage, and so on and so forth. Now, if we all had the same bog standard car or fastener, any innovation would quickly die out and no one would bother investing in any of the research or development to make higher performing fasteners. So, but we still need to do this under a robust testing and assessment condition, and therefore to ensure that the fastener will function for the specific service criteria. Again, you can think of a parallel analogy for the crash test of all cars. So all cars must go through a crash test to be deemed roadworthy, and this is essentially what it is for fasteners. So we need to establish a quality assessment and control parameters by third parties, and we need to ensure that there is compliance with those. So the assessment will capture the behavior of the entire system and the entire connection, and to to the testing regime laid out in the European assessment documents. And the idea is that the evaluation will check with respect to the working principles of friction, keying, and bonding, how the anchor will perform. Okay. Now this differs to what you would see in any test report by a random laboratory. So any manufacturer could go to a laboratory, claim to have a certain value, publish that in their catalog, and you would see that and be, oh, one anchor can achieve 100 kilonewton, and company Y is producing another one which can only do 50. Why wouldn't I take 100? Okay, I select 100, but the problem is that the performance is varied, and there's no audit, there's third-party audit, neither is there any quality control or assessment. So it's important to distinguish between a proper assessment and just a random test report. Okay, so many important values that are used in the design are established along the testing journey, and some of which have no theoretical equations that can be used by the designer. Let's take mechanical anchors, for example. We cannot calculate, there is no formula to calculate the frictional force that resists pull-out failure. And so we need to test for it. For chemical anchors, we do not know the bond stress that will resist failure unless we test the mortar itself. To make things more interesting, every fastener, even from the same manufacturer and the same family, will have different load values, different performance values. So it's important to categorize them, test them out, and publish them as well. The assessment documents must also cover deviations under installation conditions, which almost always occur on site during the service life of the fastening. Okay, so the contractor could follow the manufacturer guidelines, but install the fastener with the older drill bit that's slightly worn out. What would happen to the performance then? Another scenario is, what happens if we apply a little bit more torque or a little bit less torque than the installation instructions state? What happens then? So essentially, the idea is we need to understand all of these conditions in a tested environment first, and then translate them onto the field. Another very interesting thing is what happens if a crack suddenly forms in concrete, which it's bound to do. As you design the concrete to limit state, you expect it to crack over the service life, and this will happen. What happens when it intersects the anchor's position? So the assessment acts as proof of the fastener's robustness under different conditions, such as seismic, fire, fatigue, even static conditions as well. So to sum up, we can cluster the regulatory framework for post-installed steel to concrete connections into three sections. Firstly is the fastener's assessment criteria. So whether it's mechanical or chemical, it goes through a separate testing regime, which then gives you the technical data, also known as the ETA, and then you can design with the state-of-the-art design standard today is Eurocode 2.4, and then we move on to installing it. Okay, so we now know that design and installation are inextricably linked, but how do you link them? Okay, so the partial safety factors that you've used and the approval data that's been used is entirely meaningless if the installation is not per the manufacturer's instructions or the tested instructions. Okay. So going back to our example, once we've selected the right fastener based on the ultimate serviceability and durability conditions, and then we design to Eurocode 2.4, we need to translate this intent onto the site, and this is what we do with specifications. Guidance on on these specifications, how to specify a fastening, can be found within the same Eurocode 2 Part 4. And this is the biggest advantage designers have. In the project works, you can state whether the assumption of the nature of the concrete, and then we also, what's the existing strength class, the grade. Are we looking at an fastening in an M30 base material, an M50, so on. And also in the detailed drawing, we publish the specifications can include the number of the connections, the number of the fasteners used in the connection, the manufacturer, the type, the geometry, and many other things there as well. And what's really crucial to understand is the engineer's approval is required if one anchor is being replaced with another. This is quite important. So let's say you as an engineer specify anchor X, but the contractor proposes anchor Y. What would you do in this case? Ideally, we would go back and redesign anchor Y the same way we did anchor X. Of course, anchor Y will have its own separate ETA values, so you'd redo that design as well. So you'd have to go through the entire manual process, which can be quite tedious and cumbersome, and it might not work. So this would be the ideal way to do it. Now, just visualize how much time you have to do that in your day-to-day activities. I'll leave that as food for thought for you. So a specification that captures all these details not only standardizes what the project team and sees at site, it raises the level of the construction industry massively as well. And it can also save on the work required, the expense, and worry that might occur later in the project. It also protects professional reputations. So let's move on to installation. Now that we're on site, we have the drawings, we have the specifications. Let's move on site and familiarize ourselves where these specific instructions can be found and why they are relevant. So while the installation is not the task of the engineer, it is important to understand that the same design that we used for, the same document that we use for design, i.e. the ETA, also contains the installation steps. And here you can see on the right-hand side of your screen, just a few snapshots from that ETA for a particular anchor, okay? And it's crucial to understand that deviating from these conditions kind of nullifies the design entirely. So the ETA acts as a single source of truth for both the design data and the installation instructions. And the way we install fasteners should be done with trained installers under the right level of supervision, and failure to do that can result in significant loss in performance or even failure after several years of usage. And yes, failures do happen, as is the case in Uster in Switzerland back in the 80s, the Boston one we've covered before, and the one in Japan in the Sasago Tunnel not so long ago, all highlight this can still happen anywhere in the world. So let's go to installing this, okay? And based on the chemical or mechanical fastener we selected for our base plate at hand, the steps are really not complicated at all. So it starts by first scanning the existing concrete for reinforcement inside. Remember, we want to prevent damage to the existing structure as much as we can. And then comes the drilling process, then followed by the cleaning, the injection of the mortar if you're selecting a chemical fastener, setting the anchor, and then torquing it. Now, it's quite simple, right? So you might think, well, what could go wrong in each step, Amol? Why are you telling me all of this? Well, firstly, if you have an incorrect diameter for a drill bit, let's say at site, the specific drill bit required to install the anchor is not there, and the larger drill bit is used, what could this mean? Well, it means that the mechanical fasteners cannot develop their friction and keying forces. The chemical mortar might be unable to spread the bond evenly, spread the bond stress from the rod into the base material evenly, and your entire design values might be nullified. Okay, but the bigger problem actually comes on most sites is cleaning. Now, cleaning is a tedious task of the borehole, but it's a very necessary task, particularly for chemical anchors. Chemical anchors are extremely sensitive to a lot of the dust and debris that is caused by drilling. And if we don't clean these holes properly, there will be a failure in bond for sure. And you can see that over here. Now, the next part also comes to the injection of chemical anchors. And here, if we don't inject uniform, if there are air voids like the one you can see over here, I will just zoom in. You can see there's little patches of different colors here. This will also lead to the bond being unable, the mortar being unable to distribute the load onto the concrete itself. Now, setting is usually not a problem. You can, unless it's overhead, in which case you need to take special care. But lastly is the relevance of torque. And oh boy, this is also another very big important topic for mechanical anchors in particular, because as we mentioned in the beginning, if you don't torque the mechanical anchors to the right value, they will not develop those friction and keying forces itself. And also your base plate will not be clamped onto the concrete with sufficient force. So therefore you will have a premature failure in that case as well. So the ETA requires strict adherence to the torque values, otherwise they invalidate the design itself. Okay. Fortunately, there are some risk mitigation measures that we can take to reduce the risk of poor installation, and these are split into two categories. One is preventative, and the other is corrective measures. So under the preventative measures, the manufacturer can provide installer guidance and provide guidance to the contractor to install the anchor. So upon completion of this training, and which includes supervised installations, the installer is then certified to take on the task themselves. Also, several manufacturers provide ETA-approved innovative tools, such as impact torque wrenches with adaptive torque output that consign the spanner and torque wrench to the dustbin, hollow drill bits that drill and clean at the same time, preventing the need to clean and also preventing mistakes from cleaning, and high-powered battery dispensers that eliminate the voids inside the boreholes. So as a corrective measure, you can also do on-site testing to validate the installation quality. So let's summarize what we've covered so far. On the right-hand side, you see a very convenient little flowchart that you can also use to design and specify the anchor, and then based on where you are in the installation chain, recommend the right tools that comply with the fasteners ETA and allow the contractor to finish the job faster and without any mistakes. And so to do that, we specify with as much detail to avoid ambiguity, excuse me, and we also request the contractor or installer for proof of correct installation via on-site testing. Okay, so where to from here? So what all resources do we have to support designers and engineers, not just for the fastening of steel elements to concrete, but also concrete to concrete? And here, I'm very happy to introduce to you the Postinstall rebar book, and for base plate connections and for concrete to concrete connections. It's quite comprehensive, and recognizing the lack of design and installation guidance on this topic, subject matter experts from across the world in Hilti, under the leadership of Kamalika Kundu and Prashant Sathe, aim to disseminate this knowledge through a fair and unbiased perspective through practicing engineers such as yourselves. The book contains several real-life cases provided by structural engineers across India, and is intended for use by academics, students, anyone who is wishing to select, design, and install post-install fasteners or rebar. So in the chat window, you would have probably seen a hyperlink from where you can access this ebook. So feel free to check that out.
Yeah, there is a link which has been posted in the chat, which can be used by you to access your free e-copy.
Thanks, Karan. And the next tool we have is Profis Engineering. It's the second resource we provide. It's by Hilti's online design fastening software. And this allows you to design the entire connection, not just Hilti fasteners, but also the base plate, the stiffeners, the welds, and it has a very powerful finite element computer to do that as well. And so this is something you can see. So you can import your loads from your analysis programs, such as StatPro, ETABS, into Profis Engineering, and then you can design the entire connection using the software, and as an output you can export it as a CAD file. or a BIM object itself. So the idea is we want to enable designers in the industry to reduce the time they take to design these connections, which, as you can see, sometimes based on the feedback we've received, can take well over 60 minutes. We want to reduce that and help you reduce that to 10 or 15. So please, you will see another link in the software itself, in the chat window to access the software. So please feel free to check that out as well. And with this, we can conclude the section of this webinar, and I hand it back to our moderator, Karan.
Thank you, Amol. That was really nice of you to cover all the resources which the audience can look up at. And we have come to the end of this webinar, but there are a few questions that have come from our audience. I would like both our panelists to answer these questions. I will read out the questions to you. So first, we'll be taking the questions from our rebarring session. And these questions are for you, Dr. Janicio. So the first question that we got was from, just give me a second, let me pull up the question, was from Mr. Pinaki Banerjee, and he wants to know what to do in case we have to install chemical rebars in structures that are very old and there are no as-built drawings available. There is an issue of how do we drill without cutting the reinforcement if we don't know where the reinforcement is placed.
So in general, before even designing a connection with post-installer rebar, will be recommended to have a clear picture, as much as possible, of course, of the situation of the reinforcement existing member. Using, for instance, the existing drawing if available, but more reliable, definitely there are some reinforcement detection methods that will help to assess the presence of reinforcement. One problem could be, right, as mentioned, that of course you want to avoid to cut existing reinforcement because it might be decisive for the load carrying capacity of the existing structure, or we want, in the case, for instance, of lap splice, ensure that we install the post-install reinforcement close enough to the existing reinforcement to allow the non-contact splice to work.
And Dr. Janicio, in continuation of that question, there is a common situation that two concrete elements are cast during different time zones. So there could be an issue of shrinkage stress or differential thermal expansion, which might lead to ingress of moisture along the interface. So how can we take care of this issue?
Yes, to tackle this topic, there are no specific Hilti solution. I think there are situations, of course, which depends quite a lot from the application which is meant and need to be considered with appropriate pouring of concrete and as a specific loading case if it is required. Specifically, for instance, in the TR 66, the document issued by EUDA to design shear friction interfaces, where one might have a quite large surface of new concrete, that the problem of the lamination of concrete due to shrinkage is accordingly considered. And in that case, it's really meant, well, that the arrangement of the dowels of the connectors along the perimeter of this interface must fulfill certain design requirements, exactly to avoid this topic.
Sure. Thank you, Dr. Janicio. These were the two questions. There are some more questions that have come, but in the interest of time, I would like to take a few questions on anchoring. So Amol, there is a question which is asking about how can the design needs be taken care of? What is the software that can enable the user to make sure that is taken care of?
Sorry, was on mute. The design requirements can be taken care of by your first principle designs or by using a software package for that, such as StatPro and ETABS. And then you can get the loads for your static or seismic load combinations from there, plug those into the Hilti software such as Profess Engineering. Other manufacturers may have their own software, so you can do that, I'm sure, with theirs as well. And then you can design the connection based on those requirements. I hope I was able to get the gist of the question.
Yeah. Second question talks about how to take care of the seismic requirements when it comes to anchor design.
Yeah, okay. So there are two ways. The first one is in the testing phase. So for example, when you test in the ETA, the assessment document has a certain crack cycling test. So the cracks will open and close and when the anchor is positioned in there. So, and then whatever is the capacity or the residual value is then published in the ETA. And now that's the testing phase. Now in the design phase, you also have under the Eurocode 2 Part 4, and you have certain reduction factors that you apply to each of the individual failure modes. So that, for example, for concrete cone failure, you have a reduction of, let's say, 25%. And this is all documented in the Eurocode standard. So there are two ways of ensuring that: testing and the design document.
Thank you. I'll take two more questions quickly. So one question is with respect to, is there an extra locking mechanism for cyclic loading connection or hanger type overhead connection?
So for overhead, I believe this is relating to the lock nut, right?
Correct.
Yeah. So there is a way where you can either double nut or you can use a special type of washer that allows the anchor, that allows it to move. I don't have a picture of this on screen, but yes, there is something available that allows this condition to happen.
So last question for you, Amol. This is related to installation. So the question is, in case of chemical anchors, how much amount of chemical should be filled in a hole? And is there a way to know the amount of chemical which is already filled in the hole when a structural engineer is out there for inspection?
Yeah. So fantastic question. So when you're on site there and you're watching the installer or the contractor do the job, the key thing is that you must always fill the hole about 2/3 of the way up. So that means is, let's say you calculate you don't have to do this. The idea is the dosing is calculated with the volume of the mortar that needs to be injected inside the hole. And for this, we need to understand how deep the hole is going. So there's no fixed value. So let's say you have to drill 100 millimeters inside the concrete. So that, based on the diameter, gives you obviously a cylindrical volume. We take at least 2/3 of that, fill that in, and then as the engineer, you should be watching this very closely. So as the rod is pushed in, there should be an overflow or a bleed out of the chemical. And this means if you see the chemical forming on the outside of the concrete borehole, that means that it has been sufficiently done. But just be mindful, because we have seen a couple of cases where the installer is quite clever, wants to save on the chemical, and will just will just pour a little bit of chemical on the outside to show you. So you must ask the person to do it in front of you. So watch out for that bleed effect.
Thank you, Amol, and thank you, Dr. Janicio. It was kind of you to answer all the questions. There are some more questions. I would urge the participants to reach out to us over our platform, Ask Hilti. We will post the link of this platform in the chat window. You can post your questions there. With this, we come to the end of our session from our panelists. I would like to take this opportunity to thank Institution of Engineers for providing this platform to Hilti to talk about post-install connections. And I would also like to take this opportunity to thank Mr. Narendra Singh, Mr. V.B. Singh, and Dr. Nilanjan Sen Gupta for their kind support during this full webinar. Lastly, I would like to invite Dr. Nilanjan Sen Gupta for the vote of thanks.
Thank you. I, on behalf of the Institution of Engineers India, sincerely thank our esteemed panelists for this mesmerizing webinar, which kept us glued to the screen for the last 2 hours. Mr. Amal Singh, Technical Marketing Manager Structural, Hilti from Singapore, and Dr. Janicio, Project Manager, Ports and Approvals, Hilti from Germany, for enlightening us with their lucid deliberations and discussing the most important and contemporary topic on fastening systems in concrete construction. Both of them elaborately guided the practicing engineers who have to design different types of fasteners in their projects, as well as for academicians and students who are interested in this topic. It is obvious that in absence of national standards in India, it becomes difficult for the engineers to design the fastening systems, which are also an integral aspect of the structure. The case studies to showcase practical applications of these innovative technologies have definitely enriched us. In fact, I have personal experience of using the technology and services of Hilti when I was working in a power utility about 15 years back, and they helped us in installing some anchoring fastener bolts in concrete foundation of a steam receiver of an old power generating station within a limited time span of 2 hours only, and we could avoid total shutdown of the power plant at that time. Thank you for that service by the Hilti. I am sure that all the participants have been immensely benefited by today's deliberations and interactions, and in coming years, we may think of a national standard for fastening system in concrete construction. I also offer my heartiest thanks to Mr. Karan Khanna, Manager, Software and Services India, who steered the entire program very nicely as the moderator. Our President, Engineer Narendra Singh, and Chairman of Civil Engineering Division Board, Mr. V.B. Singh, are the sources of inspiration for all of us for such technical activities. I sincerely thank both of you, sir. I thank all the council members and division board members of IEI, corporate members of IEI, and other participants who have joined this webinar and also enthusiastically interacted with the panelists. I have seen that some of the participants have shown keen interest in the topic, which is really encouraging. Any technical activity has no meaning without the active involvement of the audience. Thanks to all of you. Last but not the least, I thank Mr. Devaraj Thakur of National Skill Development Forum of IEI, Mr. Tanmay Chakraborty, my colleague, and my other colleagues who have worked behind the scene to make the webinar a success. With this, I seek permission of our Chairman of Civil Engineering Division Board and our President, the panelists, and the moderator to end the session. Thank you. Good night to all. Please take care of your health and stay safe in this COVID situation. Thank you. Thank you all. May we end the session, sir? Chairman, sir. Okay, sir. Tanmay, please end the session.